notes. I just want to babble about a couple things really quick. So your exams, they're graded. I just haven't put them in Blackboard yet. So those will be up tonight. And also, I'll be putting on any of the other missing grades that aren't in there yet. And I'll give you an updated, current grade so you have an idea of where you're at. I'll also upload a grade calculator, so you'll be able to essentially put in the grade that you have so far and play around with grades on the final to figure out, if you want your grade to land in a certain spot, what you would kind of need to be able to do that. So that'll be all in tonight. Tomorrow morning at the very latest, but it should all be up tonight. That's my goal for having done before I go to bed tonight. All right. So also there is one final homework assignment. It's up on Wiley. And because I didn't want to, make you feel like I'm trying to have you do homework over Thanksgiving break, it's going to be due next Thursday instead of Tuesday. If you would like to pretend that it's due on Thursday for your own sanity, go right ahead. But it's technically due on Thursday to give you a little extra time, so you don't necessarily have to think about it over Thanksgiving. Also, if you don't already know, you possibly know already because it's the schedule. But so we have, of course, our class today. We'll have a class next week on Tuesday. And that's going to be, I'm trying to make it just a review day. I'm going to hopefully have something created and planned for us to do that day. But if you have questions or people want to go over certain topics, I don't mind being derailed from what I come up with. I'll be posting probably after Thanksgiving break a review sheet for the final, kind of like I did for all of the other exams. Excuse me. I'm not entirely sure the format of the final. Of course, it's going to be online because all of them are online this semester. But I don't know exactly, how much of it's going to be multiple choice, how much of it's going to be something else. One's never taken an exam on Blackboard before, or well, a quiz on Blackboard, nothing on Blackboard for me. If I'll be posting like a dummy test, it's probably just going to be a bunch of old quiz questions, just so you can kind of see how the exam format works on Blackboard in case you've never seen it before. So I'll put that up next week as well. And so essentially your final, it's in the syllabus, but in case you aren't aware, your final is Tuesday, December 7th, the 8th at 4 p.m. So essentially that's when it'll pop up on Blackboard. You'll have a 2.5 hour time frame to do it because that's the time frame that the university gives us. I usually try to write around an hour and 45-minute exam. So a little bit longer than a normal exam for you guys. But it shouldn't take you the full 2.5 hours. It might, depending on how fast you work, but it's not like I've written a 2.5 hour exam. So that's the thing. I talked about the homework. Talked about this. I know. We'll talk about the final a little bit more next week. Hopefully I'll have a better idea of exactly what it's going to look like. But I haven't put much thought into that yet. So anyway, so that's that. So today we have, we're trying to cover 5.4 to 5.5 notes. Hopefully we're going to get through them all. So let's just go ahead and get started to try to do that. Let me reshare this just in case people can't see it. And here we go. So way back when we talked about the units and kind of the interpretations, and we did like the meanings for statements involving derivatives. So essentially we have to do the exact same thing, but for integrals. So remember that the integral is technically a limit of a Riemann sum. So we had this, really scary notation from 5.2. So it's a limit of a Riemann sum. But if you think about what a Riemann sum is doing, these are, rectangles where you essentially have an x value times a y value, right? A width times a height. So essentially, because this sum since that delta t can be thought of as a small difference in t or x or whatever your variable is, then essentially the terms that we're adding up in that Riemann sum can be thought of as a product of the form of something f of t times a difference in t. So kind of, what I did just here instead, but I wrote x's instead of t's. So that essentially sets us up for the units of the integral. If this is a sum of things that are like x values times y values, then the units of an integral are going to be the units of f of x, or f of t, or f of whatever, multiplied by the units of x. So if you're ever asked to find the units of an integral, it's the units of your y values times the units of your x values. One other thing to note is that the units of the a and the b, those bounds, so the units of the bounds are equivalent to the units of x. So whatever the units of x are, that's going to be the same units as those bounds. So say, for example, we had a velocity function, some f of t, and the velocity was in meters per second, and the time was therefore in seconds. Then if we had an integral of that velocity function, the units of that integral would be meters per second times seconds, so just meters. So we take our units of our f times our units of our t, or our x, or whatever our variable is. So let's look at a couple examples of interpreting things like this. So say we have C of t representing the cost per day to heat your house in dollars per day, where t is measured in days, and for context purposes, t equals 0 is going to refer to January 1st of 2018, and we want to interpret the integral from 0 to 90 of C of t dt. So first off, let's talk about units. So the units of this integral, well, we need the units of C of t. Well, that's dollars per day. Dollars per day times the units of t, which is just days. So essentially those day units are going to cancel each other out, and this is just going to be in dollars. So essentially this integral represents some amount of dollars. So if we try to think about what that's going to mean in this context, well, we're talking about the cost to heat your house. So this is going to be an amount that you have to pay to heat your house. So if we want to try to say this and interpret it, well, actually, sorry, one thing before we get to the interpretation. The units of the 0 and the 90, since they match the units of t, those are going to be days. So essentially we're going from day 0 to day 90. So there's a couple ways that we can interpret this. Let me try to save a little bit of space down here. So how I would phrase this, because I've been doing this for a while and I kind of know. Oh, no, there's no quiz today. Your last quiz was way back when. We're done quizzes. Anyway, so since I know how these go and I know how to interpret them, I'm gonna kind of go with the better English way. But then I'll show you the kind of cookie cutter, always works, but sometimes sounds really bad way. So if I wanted to interpret this in kind of a good English way, and still not the best English, but anyway, I would probably say something like the cost in dollars to heat your house for the first 90 days. Maybe I'll even say 90 days of 2018, because t equals 0 starts at January 1st, 2018. So I'm essentially taking the first 90 days of 2018, and that's going to tell me the cost to to heat my house for that time. Now, again, that's kind of a good way to phrase it. When we're doing these, you can always phrase it. So I'm even going to write it as cookie cutter. The cookie cutter way. That kind of always works, but usually sounds really bad. Is you can say a change in, and then it's kind of like you got to find the right context. In your units between x equals a and x equals b and whatever their units are. So maybe I should be clear. Your integral units in that first space and your x value units in the second space. So if I were to phrase this in the cookie cutter language, I would say the change in cost in dollars. Well, maybe I should say the change in cost to heat my home. The change in the context here is cost to heat my house in dollars between t equals 0 and t equals 90 days. It sounds much worse, but it gets the point across, and that's all I care about. So you could say change in the cost to heat your home in dollars between x equals 0, t equals 0 and t equals 90 days. So that's kind of the way that always works, but usually sounds really bad. But just like with the derivative interpretations, as long as you get the point across, I don't really care much for whether it sounds like good English. Questions, concerns about that? Before we do a couple other ones? Okay. So say we want to interpret a couple more. Let me try to leave that cookie cutter language in there. So say we have the integral from 1 to 3 Vt dt, where Vt is in meters per second and t is time in seconds. So we essentially have a velocity function and seconds. So our units here for our integral are going to be meters per second times seconds. So that's just going to be in meters. So our integral units are just meters. So say I want to do the cookie cutter language here. I could say change in. Now this is meters, so this is a distance. So this would be the change in distance in meters between t equals 1 and t equals 3 seconds. If I wanted to phrase this the tiniest bit better, there's not a great way to phrase this one that I can think of, but you could say something like distance traveled. Is it 2 L's? I don't know. In meters between, I don't know, the first and third second? That sounds a little nicer. You don't need both. I'm just trying to state a couple ways you could phrase this. That first one is kind of that cookie cutter, doesn't really sound good, but gets the point across language. And then the second one sounds a little better. It's still not great, but still gets the point across. So our integrals are always a change in something. So here it's a change in distance. I do want to say you need to be a little careful. So say I wanted to say something like, let me write this in red because it's not really right. Distance traveled in 2 seconds. If you tried to say something like distance traveled in 2 seconds, that wouldn't quite be good enough because what 2 seconds? Is it the first 2 seconds? Is it the last 2 seconds? Is it the middle 2 seconds? What 2 seconds? So if you said 2 seconds between t equals 1 and t equals 3, that would be okay. It sounds a little silly, but it would be okay. But just be careful when you're phrasing it to make sure that the bounds do get in there somehow. So yes, this is technically a difference of 2 seconds, but it's a 2-second change starting at 1. So you kind of need to, if you're trying to phrase it as like a difference between the bounds, make sure you at least tell them where the bounds start. So just be careful of that. Or you can just use the cookie cutter language and have it sound really bad, but at least get the point across. So next one, if there are no questions on that one, wait like 5 seconds. Okay, so say we want to do the integral from 2005 to 2011 of f of t dt, where f of t is the rate of population growth in billions of people per year, and t is time in years. So let's talk about units first. So we need the units of f of t. Well, that's billions of people. Billions of people. Maybe I should, hold on, write it like that because this is a rate. So I'm going to want to do that year. There we go. Billions of people per year times the units of t, which is years. So those year units essentially cancel each other out. So this integral is just going to represent an amount in billions of people. So say I want to do the cookie cutter language here. I would say change in, and then I kind of have to figure out the context that this integral is talking about. Well, it's talking about an amount of a population. The integral is an amount of people, so it's going to be a change in population in billions of people. Between 2005 and 2011. Now, of course, here I didn't write 2005 years and 2011 years because the context of years is kind of, implicit in there. When I write 2005, it's the year 2005. But just be careful when the units aren't, kind of known in the context like that. Make sure you state them. Like in the one above, I said t equals 1 and t equals 3 seconds. Here I don't use years because it just kind of makes sense. For the final, will we have questions at us? Yes, so this material that we're going over today is fair game for the final. Yeah, Camden, all of the, let me type it in chat because your Wi-Fi is going in and out and you can find it in the chat later. But Camden, and I'll say it too as I type it. So recordings are posted on Blackboard under course, I can't spell, content, I really can't spell, content and lecture recordings. So on Blackboard, there's under the general course content, there's a lecture recording folder, and all of the recordings go in there eventually. So that should be up hopefully tonight, possibly tomorrow morning if I forget. But yes, it will be there. All right. Questions on this before we do a couple more? And I think I already said it, but yes, the stuff we're going over today is fair game for the final. All right. Slightly different type of question for this. So a man starts 50 miles away from his home and takes a trip in his car. He moves on a straight line and his home lies on that line. His velocity is given in the figure. Also, let me draw this because I feel like that t-axis is not very clear. So that's the t-axis. So we want to know, well, first off, so this is his velocity function. So essentially any velocity that's positive, we're going to treat that as him traveling towards his house, and any velocity that's negative is going to be treated as him driving away from his house. So essentially he starts 50 miles away, and let me write that down here because I'm going to need to scroll down a little bit in a second. Starts 50 miles away. And so he's going to drive towards his house for the first 2 hours, and then he's going to like turn around and, I don't know, realize he left his kids at the cabin at the lake, and then he has to travel back away from his house again. Hopefully they didn't forget kids at a lake. Anyway, so say we are asked to find when is the man closest to his home, approximately how far away is he then? So he's going to be closest to home before he turns around and starts going in the opposite direction. So essentially, if he starts away from home, starts heading towards his home, he's going to be the closest to his house before he turns around again. So he turns around at t equals 2 because that's when his velocity changes from positive to negative. So when the velocity changes from positive to negative, he's no longer going towards his house, he's now going away. So hopefully that worked, Cameron. Let me know if it didn't. So he's going to turn around at 2. So the closest to his house is probably going to be when it's been t equals 2 hours. The time before he turns around. So we want to know how far away from his house he is at that point. So we essentially need to know how far did he go in those 2 hours. Now, since we're given velocity, if we want to know the distance he's traveled, we want to know essentially the antiderivative, but we don't have an actual equation here. So remember, an antiderivative and an integral is area. So instead of trying to find something we can't find because we don't have an equation, we can find how far he traveled by finding the area underneath of the function between 0 and 2. Now, we could do a Riemann sum if we really, really wanted to, but I would say let's just do our counting boxes technique. I know that's not everyone's favorite, but let's just try to count the amount of boxes we have here. So if we notice, there's kind of like almost half a box in this first piece, and then almost half a box in this second piece. So together, their powers combined. That makes about 1 box. That was stupid. I shouldn't have said that. So there's about 1 box underneath of that piece. So I can essentially say that the integral from 0 to 2, let me call this v of t, of v of t dt. So there's going to be 1 box. But remember, when we're counting the boxes, we can't just count the number of boxes. So the answer isn't just 1. We have to figure out how big each box is. And we have to multiply the number of boxes by that. So if we look at kind of the units on our axes here, we have a 1 by 30 box. So essentially the area of each box is a 1 by 30, and that would give us the area per box. So remember, we have to multiply the number of boxes times the area of each box. So we essentially have 1 times 30. So essentially there's an area of 30. So let me write it like this. 30 area. I know that sounds stupid. Now this is representing miles. Because if we were looking at a integral and we were doing miles per hour times hour, then the units of this integral are in miles. So essentially, finding the area underneath of that tells us that he traveled 30 miles towards his house. Now, we're not quite done this question yet because we want to know how far away, how far is he from his house. So if he starts 50 miles away and then he traveled 30 miles towards his house, he starts 50 miles away, he travels 30 miles towards his house, so we're going to subtract it. He ends up 20 miles away. So we had to find the area between 0 and 2 to find how far he traveled. And we were stopping at 2 because when the velocity turns from positive to negative, that means he turns around. And then we had to also consider the fact that if he started 50 miles away from his house and then he travels 30 miles towards, that means he actually ended up 20 miles away. Questions, concerns about that before we do the second part? Okay. I'll wait a couple seconds before going on in case people are still writing stuff down. All right. When is the man farthest from his home? How far away is he then? So we want to keep in mind where he started because maybe he started the farthest away from home. So let's kind of keep that in our back pocket. But if we look at this graph, he's traveling away from his house essentially in this whole piece that's below the x-axis. So between 2 and 5 hours, he's traveling away from his house. So we should probably figure out how far he drove away from his house again. So let's figure out the integral. Let me try to zoom out a little bit so I can keep some of this in here. There we go. So let's go ahead and find, whoops. Since we already know the amount of area between 0 and 2, let's just go from 2 to 5. And let's just figure out how much of that area is below the x-axis there. So let's go ahead and count boxes again. So let me actually zoom in on here really quick for our box counting. So if we want to count our boxes here, we have, one full box that's right here. And then I got to start like piecemealing them together, which is always the terribly not fun part. So we have this small piece here and this almost complete piece that's just missing this little bit. Where did the 50 come from? Yeah. It's given to us in the original question, which I had scrolled past, so I understand if you didn't see it. So a man starts 50 miles away from his home. So that's why the 50 came into play, because that's just given to us in the original statement of the problem. He starts 50 miles, and everywhere he travels gets based off of that starting point. Okay, so we have, whoops. We have one box so far. Zoom back in. And we've got this little tiny area and then this area here, which is almost one complete box. So if I link those two together, that's going to get us like a second box. So let me just put 2 over here. I know it's not a full box, but let me maybe. And then between these two pieces here, those would probably make about one box if I grouped them together. So let's say between these two at the bottom here, it's going to be about a third box. And then the only spot we have left is this piece over here in the left corner, if you will. And that piece in the left corner looks to be about another half a box. I know it looks to be a little bit more than half a box, but again, for our own sanity, we're estimating here. So let's go ahead and say that this piece in here is about half a box, which means that that's half a box and we have about 3 full boxes worth, that we would get about 3.5 boxes in that area piece. But then remember, we have to multiply that by the area of each box, which we already found to be 30. They're 1 by 30 boxes. So that means that, so let me actually erase this boxes thing. Maybe I'll put it underneath to remind us where it came from. Area of box. So that means that'll give us 105. And since this is an integral value, it'll be in miles. And since all of that area was below the x-axis and any velocity that was negative was treated as traveling away from home, this would be miles away from home. So maybe let me go back up here really quick and specify that these miles were towards home. Now, once again, we need to be a little careful because we're starting at time 2 here. Now, when, sorry, my English decided to break. Words, I know how to speak them. At time 2, he ended up 20 miles away from his house. That's what we figured out in the first part. So essentially, he's starting now 20 miles away from his house, and in the time frame of 2 to 5, he's traveling an extra 105 miles away. So we would have to actually add these together this time to get that he ends up 125 miles away. So we're adding this time because he started that far away and he's going farther away. Whereas in the last one, he started so far away and started traveling towards his house. Now, again, I said at the very beginning of this part of the problem that we should keep in our back pocket that he started 50 miles away from home, but 125 is larger than 50. So the farthest he gets away from home is at t equals 5 when he's 125 miles away from home. Questions, concerns on that? There is a question like that on your homework, so if you didn't quite understand any of that, let me know. I'll wait a couple seconds in case anyone's still writing something down before we go to the next one. All right. So the next one, we've got the rates of growth of the population of two species of plants measured in new plants per year are shown in the figure. Assume that the populations of the two species are equal at time t equals 0. Now let me be very clear. The graph is not the actual population. It's the rate at which the population is growing. So this isn't saying that the populations are equal at t equals 1. Just because they intersect there doesn't mean the populations are equal. It means at that point they're growing at the same rate. Okay, now that I've said that. So the first thing we want to know is we want to know which population is larger after year 1 and then after 2 years. So first off, let me break this up. I like to break it up because it makes it a little clearer. So what we need to consider here is, first off, we're told that assume the populations of the two species are equal at time t equals 0. That's really important here because what we're able to find from this graph is only how many more we get in a time period. It doesn't take into consideration like where we started. Like in this last one, we found that he traveled 30 miles in that first part, but that didn't take into consideration the fact that he started 50 miles away, so we needed that extra piece. So here, if we weren't told that the populations were the same, we wouldn't really be able to say anything because maybe one of them started with 0 and one of them started with 1,000,000 and it barely even matters how much they grew by. But since they both start at the same amount, no matter what that amount is, we just need to compare how much they've grown by. So we can consider how many new plants they've gotten, how much they've grown by looking at the area underneath of these two functions. So if we want to compare, so year 1 and then, well, it's more like 2 years. So let me say it like 1 year and 2 years. So after 1 year and after 2 years. So if we're just looking at the span of 1 year, we're essentially comparing the area underneath of these two functions. So if I look at the area underneath of kind of this bottom function, which goes to species 2, that has an area of, this space here that I've just kind of colored in. So we've got that area, but then notice when I look at the area underneath of the other one, I get kind of way more area because I get not only the black area, but I get this yellow area as well. So the area underneath of species 1 would be the sum of those two areas, where the area underneath of species 2 would just be the black area. So which one has more area? Species 1, hopefully is somewhat clear. So since that has more area, that means that species 1 is going to have more growth, is going to have more plants added into the population. So the population of species 1, that's not how you spell species. Species of species 1 is going to be larger after the first year because it grew by more plants because there was more area underneath of that function. Now, when we look at the span of 2 years instead, so species 1 is going to, continue to grow. That's a completely different yellow. Anyway, is going to continue to grow by this much in here. So the area underneath of species 1 for 2 years is essentially all of the shaded area at this point. But then species 2 starts to grow a lot faster and gets this extra black area. Maybe I should make it a different color because I had black area already and I want to talk about it separately. Let me make it a purple. This purple area right here. So now species 2 has all this extra purple area that species 1 doesn't have. Now technically species 1 still has this kind of group of area that the species 2 didn't have, but if we compare these two parts, the shaded purple part is larger than the circled purple part, if you will. So the area that species 2 gains, is larger than the area that it lost out on in year 1. Does that make any sense? Essentially what I'm trying to say is the total amount of area under species 2, which is now all the shaded area now that I've deleted that first yellow piece. So essentially all of that shaded area is going to be greater than the shaded area under species 1. So species 2, I'm still writing in purple, species 2 would have a larger population after year 2 because it has a larger amount of area in that span of those 2 years. Does that make any sense? Are there questions about that? So since we are given the rate at which the population is growing, the area underneath of it is going to tell us how many more plants there are. And if they start with the same amount, we just need to compare how many more plants they have. So we just need to compare their areas. Questions, concerns about that? We get rid of all this shaded stuff. Okay. So the second part of this question is asking how much does the population of species 1 increase during the first 2 years? So it's essentially asking us to actually find that area. So this one's going to get a little tedious because there's a lot of boxes, but we're going to use our counting boxes technique. So let me zoom in on this sucker. Woo. And maybe zoom out a little bit if I can. There we go. So if we want to know the actual, like how much the population actually changed by, we want to know that actual area. So we want to find the area under species 1. So species 1 is this one. So we kind of need to block out this blue line down here out of our brains. So let's start by counting the full boxes. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's call that a 12th one. I know it like kind of barely gets a full one, but let's just for our sanity say that's a 12th one. 13, and then things start getting a little wonky. All right, now we got to try to piecemeal these together. Now, this is probably going to be really hard to kind of note here. So let's start kind of in the left corner. These two right here, these two, if I smush them together, they would be about another third box. So between these two, that would probably give me a 13th box. Between these two, moving to the right, between these two, that would be about a 14th box. And now we've got this almost full box and the piece down on the very left, which is almost half a box. So with them combined, one of them is almost a full box and the other one is a little bit more than half a box. That would probably be an extra box and a half. So we would end up with a total of 15.5 boxes. Is everyone okay? Why are there two 13s? Oh, Lord, no. Because I'm a dummy. So that would be a 14th. This would be 15. So this would mean 16 and a half boxes. Sorry. Yeah, I can share my screen again. So I double counted 13 like a doof. So there would actually be 16 and a half boxes. Thanks, Hannah. Is everyone okay with how I pieced those together? I know it's like a super wishy-washy way of doing things, but okay. So there's 16 and a half boxes, but again, we have to take into consideration the area of each box. So let me kind of just think about this box right here for a second. This box up here, just because it's clear and out in the open and doesn't have a bunch of stuff written in it already. So if I look at this box right here to try to figure out the area of each box, so this one gets a bit more complicated. So notice that on the t-axis, we have 4 lines between 0 and 1. So this distance for just one box would just be essentially a fourth. Nope, 0.25, not 0.24. 0.25, 1/4. And then the distance of the height here, since we essentially go a distance of 1500, but in 2 steps, that would be 750. Everyone with me so far? So the area of each box would be whatever the heck 1/4 times 750 is. We'll just take that into consideration for our final answer. I don't know why I drew this little thing here. So all of that to say that we found 16.5 boxes and an area of 1/4 times 750. So that means if we wanted to find the amount of population increase, so let me even write it as, let me name this S of t. Let me even write it as an integral. So 0 to 2 of S of t dt would approximately be 16.5 boxes times whatever 1/4, no, 0.25 times 750 is. So that's the area of each box. So we have 16.5 times 0.25 times 750 gets us about 3,093.75. So about 3,094 plants. So there's about 3,094 new plants between the first year, well, the starting point and the end of the second year. So between 0 and 2 in the first 2 years, there's approximately 3,094 more plants than there were before. Questions, concerns about that? Okay. So, moving on. I think, yeah, that's the end of 4.4. So that's 4.4. Interpreting like we did at the first page, and then there's sometimes some other types of questions where it just asks you questions about it, and you kind of just need to recognize that the interpretation is essentially telling you how to find it. So here, since we were given the rate of population change and we actually wanted to talk about population, we wanted the integral, not the actual like value of the function or anything like that. So then we've got to talk about 5.5. So let me just try to note that in our notes is where 5.5 is going to start. So 5.5 is about the fundamental theorem of calculus again. So we've kind of talked about it a little bit. It was what we used to do those definite integrals by hand, the f of b minus f of a thing. So if f of t is a rate of change of a quantity, then the integral from a to b of f of t is the total change in quantity between a and b. So this is kind of like where that cookie cutter language comes from for the interpretation. And then here is the thing that we were using for our integrals. So we got to talk about this a tiny bit more. So essentially this means that we can either solve for that f of b or f of a. And this is especially going to be helpful when we can't actually solve that integral by hand. So specifically for the final, just in case you don't have a calculator that can do integrals, I'm going to show you in a second Desmos. If you've never used Desmos before, it's pretty great. And Desmos can do integrals for you because on your final is going to be open note, open resource, so you'll be able to use Desmos. What am I saying? So there might be some questions on your final like this where you can't do the integral by hand and you have to use a calculator, so you'll be able to use Desmos. Anyway, but essentially the reason that what this is trying to say is we have this thing telling us that the integral is equal to f of b minus f of a. But essentially that means that we could solve for either one of these. Yeah, that's exactly how it's spelled, D-E-S-M-O-S, Desmos, yes. So essentially, if I wanted f of b and I wanted to get f of b by itself, I could just add the f of a over to the other side. And as long as I knew what that value was, I could then have f of b. Or if I wanted f of a, it's kind of similar, but there's a tiny bit extra algebra to it. So I would essentially start by doing the same thing. Add f of a over to the other side. But if I want f of a by itself, but positive, which is why I added it over to the other side first to make it positive. And then we can get f of a by itself by subtracting that integral over to the other side. Now, technically, you could like memorize these forms. I don't have them memorized. The way I do it is I have the fundamental theorem of calculus memorized, which I think most of you kind of at least have partly in your brain already. You kind of remember the f of b minus f of a thing. And then I just find it this way. But technically, you could memorize those two forms, but I would, it's not worth your time. Just remember the fundamental theorem of calculus and do some algebra. But anyway, let's look at an example. So say we have a bacteria colony initially has a population of 14 million bacteria. So we're gonna need that. Suppose that t hours later, the population is growing at a rate of f of t equals 2 to the t million bacteria per hour. First thing I want is to give a definite integral that represents the total change in the bacteria population during the time from t equals 0 to t equals 2. So, well, up above, we were told that the integral tells us a total change. So if we want the change in population, we want the integral from 0 to 2 of the rate of population change, which we're given as 2 to the t, and dt. And I gave us way too much space for that part of the question because that's all it wanted. It's literally just that. So then say we actually wanted to find the population at t equals 2. So what we actually want is we would want the antiderivative at 2. So remember, the capital letters are usually used for antiderivatives. So we would want the antiderivative at 2. Well, if I think about what this actual integral is telling me, this would be the antiderivative at 2 minus the antiderivative at 0. Now, again, this is what I mean by some of them that can't be done by hand. This integral here, we don't know the antiderivative of 2 to the t. It exists, there is one, but we don't know it. So we would need to plug that into a calculator to be able to finish solving this, which we'll do in a second. But what I want is I want f of 2. So let me get that by itself first. What is that? That's never happened before. Oh my god, zoom back out. So, stop it. What is happening? I just want to draw a squiggly. There we go. If we add f of 0 over to the other side, that was really... Then we get what we want. So essentially what we can do is we can use a calculator or Desmos. I'll show you how to use Desmos in a second. And then we would need to know what this f of 0 is. Now we actually do know what f of 0 is. So this would be the population at time 0, so the initial population. But we're told in the original statement of the problem that the population started at 14. So this f of 0 is going to be 14. Okay, and now let me show you how to use Desmos in case you've never used Desmos before. Desmos is awesome. So I gotta do that. I gotta do this. Oh, it's angry at me. Gotta do this. First off, if you can't find it, you can literally just Google Desmos, D-E-S-M-O-S, and just click on the first thing. If you go to their main page, it'll look like this, and you can just hit the graphing calculator thing. So first off, this can do a ton of stuff. You can just graph them, and it'll point out things like where they intersect the x-axis and all that jazz. But anyway, if you want to do an integral, you start typing integral. So like int, and boom, it changes into an integral. Woohoo! And then you just like fill it out. So 0 up arrow 2 to the t. Now on this one, unlike your calculators, you can type in whatever variable you want as long as you're consistent. So if you did 2 to the x dt, then things would be weird. But as long as you're consistent with the variable, it'll do it. So the integral is 4.328. Hooray! We did it. So that's how you can do it in Desmos. You just start, literally, you'll type in int. Now it didn't do it then because I put a quote at the front. But if you start typing in int, they'll change into an integral symbol, and then do it. I'll probably put a note on Blackboard about that, in case any of you forget how to do it, and you do it on your final. But anyway, let me get back to notes. Oh man, I've already forgotten. What is that? 4.328. 4.328. And of course, you can still use your calculator. If you have a calculator that can do it, go right ahead. I'm just saying for those people who don't have a calculator who can do integrals, Desmos can do it. So the answer that we want for this question is 18.328. That is the population at time 2. Questions, concerns about that? Okay. Let's do another one then. So this one doesn't have as much context as the last one, but it's the same kind of idea. We're given the original function is x e to the x squared, and we're given an antiderivative at 0, and we want to find the antiderivative at 3. So the thing about these types of questions is you're essentially always going to be asked to find an antiderivative value, and you have to be given another antiderivative value. And so essentially, the bounds of your integral are always going to be the antiderivative value that you know and the antiderivative value that you want. And they always go in order. The smaller number goes on, excuse me, the smaller number should go on the bottom no matter what. Well, for our sake, just always put the smaller number on the bottom. You technically don't have to, but let's just try to be good about that. Usually the smaller number goes on the bottom. Anyway. So just to be really, really clear here for a second, hopefully. So if this had instead said f of 1, this would be a 1. Like it's not always 0 to the thing, it's the number you have to the number you want. So just be careful about that. But anyway, so here, if we think about the fundamental theorem of calculus, this would be capital F of 3 minus capital F of 0. So if we want to solve for this, we're going to add the f of 0 over to the other side. And now we know or can find those values. F of 0, we're told that's 1/2. I'm going to write it as 0.5 just because the integral is going to be come out to be a decimal. So I'm just going to change that to a decimal just because I want it. And then if we use either a calculator or Desmos or whatever you like to solve that integral, you'll get that integral, because again, this is another one that we can't do by hand. There is a process that usually we would actually cover in this class, but we ran out of time, which is fine. We didn't need to cover it, but usually we would learn how to do that one by hand, but we won't. But anyway, so we'll have to use our calculator for that. So we'll get 4,051.0, let me say 42. So then our answer to the question is 4,051.542. So it doesn't change a lot, but and we're done. We're done. Well, we're done now. Questions, concerns about that? Okay. I'll wait a couple seconds before we move on in case someone's writing something down. I also just remembered I'm going to want to pull something up really quick at the end of class, so let me get that set up really quick before we finish these notes. Quick. And there. And okay, so one thing that we'll use this for a lot is actually in terms of cost, revenue, and profit. So remember that the derivative of cost is the marginal cost. So C prime is the marginal cost, and C of Q, regular old C, C of 0 is the fixed cost, which remember is that the cost before you sell anything. So then essentially an integral from A to B of the marginal cost, well, of course, using the fundamental theorem of calculus would be C of B minus C of A. And so this would essentially be the cost to increase production from A units to B units. So if we wanted to just talk about variable cost, so way back when we first started talking about cost, we figured out that it's made up of two things: your fixed cost, the thing that you have to pay no matter what, and then the variable cost. How much does it cost for you to actually make each thing? And way back when we were just talking about linear functions, it was just the slope. And then we also thought about it in terms of a derivative, because the slope tells us derivative, the derivative tells us slope. The derivative tells us slope is what I meant to say. But now we also have a way to think about it in terms of integrals as well. And that's going to be that the variable cost is going to be the integral from 0 to b of the marginal cost, dq. So we can find the total cost. Say we're only given the fixed cost and the marginal cost for some reason. We would be able to find the total cost of of making B units by taking the, initial cost, the fixed cost. Essentially, let me write it like this first. Fixed plus variable. That's kind of how we presented it at the very beginning of the semester, fixed cost plus variable cost. Same kind of deal here, your fixed cost plus our new formula, our new notation, if you will, for variable cost. So I'll let you take a couple seconds to get that down. We'll do one example of this, and then I want to do one last thing. We should have enough time for both of those. Good. So say we have the marginal cost given in the graph. So we don't actually know the equation, but we have the graph of it. And we know that the fixed costs are $1,000, and we want to find the total cost of producing 250 items. So essentially, if we want the total cost, we're going to have to take the fixed cost and add on the variable cost, which we just learned is the integral from 0 to 250 of the marginal cost. Now the fixed costs we're just told that that's 1,000 right there in the problem. But we do have to figure out this this integral here. So let me make an intermediate step and say area under C prime of Q between 0 and 250. Because again, we don't have an equation for marginal cost. So we can't just find the antiderivative. We can't just plug it into our calculator because we don't actually have the equation. But we do know how to estimate it because we know that it's going to be that area underneath of that function, and we have a couple ways to estimate that. We're going to use our counting boxes technique one more time. So let's count some boxes. This will be the last time we have to count boxes today. So let's start with our full boxes. Make sure I don't double count again. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And now piecing this one together is a bunch of fun. So we have these pieces right here kind of on the left, that almost full box and the kind of tiny bit there. That's going to get us about a 15th box. And then maybe these two pieces above it will go ahead and get us a 16th box. And now it gets a bit more complicated because things start getting spaced out a bit more. This box right here and this little squiggle in the top. If I group those together, those will be about another box, so a 17th box. If I group these two pieces together, the almost a full box with the little piece above it, that'll be an 18th. So what don't we have yet? We don't have this piece over here, this piece here, and this piece here. Okay. Well, if we group this one with this piece, so I know these are all over the place. This is why this does get a bit tedious with counting boxes, but if we group those two together, that'll be about another one. So now we just have this last bit that's in the middle. Now, I feel like I should have one more than that. Did I miss something somewhere? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, I got two 18s. I did it again. 19. Oh, I can't count. I was about to say, I'm pretty sure there's almost 20 boxes here. So we're up to 19 boxes. And we just have that one that's circled in orange at the bottom. Now, to be quite honest, I would kind of accept anywhere between 19 and a half and 20 boxes. Let's just go ahead and say 19 and a half. I know that's a bit more than half a box, but it's not quite one box. If you decided to round it up to 20 boxes, I wouldn't, tell you you're wrong. But let's just say 19.5 boxes. Let's say this is, we're going to round down. So we're going to say 19.5 boxes. But remember, we always need to take into consideration the area of each box. So we have a 50 by 2 box. So the area of each box is 2 times 50. Area per box. So 19.5 times 50 times 2. Whoops. Times 50 times 2 is 1950. So that's the area approximately underneath of that function. So that will be our estimate for our integral, if this will zoom out. So we have 1,000 as our fixed cost plus the marginal, marginal and variable are like the same thing, plus our variable cost that we just estimated. So we can say that the cost to produce 250 items is approximately, 1,950. Now, the reason we've been counting boxes so much is because remember the stuff we did by hand with the antiderivatives was technically chapter 6, and this is chapter 5. So that's why we've kind of gone backwards and started counting boxes again. If you were to actually have an equation here, you could do the antiderivative method. But since we weren't given an equation, that's why we had to do the counting boxes idea. Whew, questions, concerns about that? Oh, Lord Almighty. Isabella, because I'm dumb. I can't. It's 2950. 1,000 plus 1950 is not 1950. Lord Almighty. 2950. Thank you. Any more questions about that one? Oh, Lord. All right. I want to do one last thing and then I'll let you go. But there's one type of question that is not in this notes that technically you do have the skills to do, but sometimes a lot of people don't realize they do. So I want to talk about it because it shows up on your homework. You do not have this problem that I'm about to pull up. Where'd it go? Oh, are you being stupid? There we go. So you do not have this I will be posting this on Blackboard. I'll be posting a screenshot of the problem. But you don't have this anywhere. If you want to write something down really quick, this is the main meat and potatoes of what you really need from this problem. So I'll give you like 5 seconds if anyone wants to write that down on a piece of paper. But again, I'll be putting a screenshot of the work for this up on Blackboard. So wait like 5 seconds. So we have a lab is performing tests for a new drug. They're testing how long the drug stays in someone's system. Let capital D be the amount in milligrams of the drug left in a person's body X minutes after administration. Let little d equal capital D prime the rate at which the drug leaves the body. So essentially what that's saying is that capital D is the antiderivative. So remember, capital letters are usually used for antiderivative purposes. So the capital D is the antiderivative of little d. So given the information below, evaluate the given expressions and interpret them in terms of the drug use. I'm probably going to skip the interpret piece just for the sake of time. The main thing that I want to talk about is how to find these. So we're given the information that's in that box right there. And we want to know what capital D of 0 is. So if we think about what we were just talking about in 5.5 with the fundamental theorem of calculus, if we had an integral from 0 to something of little d, then we'd have d of whatever minus d of 0, and we'd be able to solve for d of 0. Well, in the information we're given, we're actually given 2 of those. Now, to be able to use one of them, we would then have to know the antiderivative value at the other bound. So we would either need to know d of 4 or d of 7. And actually, in this case, we know both of them. So we actually have 2 choices for which one we'd want to use. They'll both give you the same answer. So I'll do both of them really quickly. So essentially, if I take the 0 to 4, whoops, this would be d of 4 minus d of 0. So if I want to solve for d of 0, I personally would still add it over to the other side so that it turns positive, because we want positive d of 0. We don't want negative d of 0. And then subtract the integral thing. Why did I write 40? Subtract the integral thing over to the other side. And then once you have it written like that, you actually know both of those values. That's kind of the point, is that they give you all of those values in the original statement of the problem. So d of 4 is 5, and the integral value is negative 3, so we'd get 8. Which is exactly the same thing you would get if you'd use the integral from 0 to 7. So let me just write that out really quick. So we would essentially do the same algebra and add the d of 0 over to the other side, and then subtract the integral value minus the integral of 0 to 7. But now we would need d of 7, which is 3, and then the integral from 0 to 7 is negative 5, which also gives us 8. So the answer there would be 8. So d of 0 is 8. I'll say the interpretation, I won't write it down. So that would essentially tell us that after 0 minutes, there's 8 milligrams in their blood system. So essentially that's the initial amount that they administer. So they initially administer 8 milligrams of that drug. Questions on how I found that? It's really just using the fundamental theorem of calculus statement and then doing some algebra to solve for the value that you want. And you can replace things in earlier. If like replacing them in first and then rearranging just the numbers makes you happier, go right ahead and do that. I've been rearranging the notation, but you can replace earlier if you want. And then in the second one, we want the integral from 2 to 7. Well, this would be the antiderivative of 7 minus the antiderivative at 2. And we actually are given both of those. So we can just go ahead and plug them in. So d of 7 is 3. D of 2 is 7. So we get negative 4. If you were thinking about an interpretation for this, it would be a total change. So a total change in the amount of a drug in their system. So essentially the change is -4. So between the second and seventh, what are the units on this? Second and seventh minute, 4 milligrams of the drug leaves the person's body. So there's a change in 4 milligrams leaving the body. But again, I'm not going to write those down. The main thing I wanted to talk about was how to find those. So there are 2 questions on your homework, very similar to those, where you're given a bunch of information and you just need to find the right way to put it together. Anyway, 5 minutes early. So we're done. We're gonna stop there. So again, next week we'll have a review day on Tuesday, and then your final is essentially the week after on Tuesday, the 8th at 4 p.m. We'll talk about the final a bit more next week. I don't know exactly the layout. I don't know how much is going to be, what type of question. I need to think about that a bit more. As soon as I know, I'll let you know. And again, your grades should be up on Blackboard by the end of the night. If you have questions, feel free to stick around. Otherwise, we're done. Have a great and safe Thanksgiving, please. And I will see you on Tuesday.